Okay, we're going to begin covering chapter 16, electrical energy and capacitance. This is where we're actually going to start getting into circuits. In this topic, you'll see that the potential energy concept is also useful in the study of electricity. Because the Coulomb force is conservative, we can define an electric potential energy corresponding to that force. We will also define an electric potential, the potential energy per unit charge, which corresponds to the electric field. Then we will be able to begin analyzing electric circuits, starting with capacitors, which are devices that store electrical energy. Let's bring up, let's share, and there we go. Okay, all of these are capacitors. There's different types of capacitors. There's some that are polarized that you have to put in the correct order. You can get large capacitors and small capacitors. You can get some that are so small that they look like just bits of a broken piece of glass, but they are capacitors. Okay, let's. Okay, as you recall, the work done by a conservative force F on an object only depends on the initial and final positions of the object and not on the path taken between those 2 points. This means that a potential energy function exists. Potential energy is a scalar quantity with a change in potential energy equal by definition to the negative of the work done by the conservative force as shown here. Both the Coulomb force law and the universal law of gravity are proportional to 1 over r squared. Because they have the same mathematical form and because the gravity force is conservative, the Coulomb force is also conservative. As with gravity, an electric potential energy function can be associated with this force. To see how this works, imagine a small positive charge placed at point A in a uniform electric field E. Okay, let's start over. To see how this works, imagine a small positive force placed at point A in a uniform electric field E, as in the figure. Let's assume for now that the electric field is constant and that the charge moves parallel to the field. As the charge moves from point A to point B under the influence of the electric field E, the work done on the charge by the electric field is equal to the part of the electric force QE, acting parallel to the displacement. Acting parallel to the displacement times the displacement. There it is. Work AB is equal to force along X times delta X equals QEX, X final position minus X initial position. In this expression, Q is the charge and E sub X is the vector component of E in the X direction, not the magnitude of E. So E sub X can be positive or negative depending on the direction of E. Note that in this figure, EX is positive. The displacement can also be either positive or negative. This equation gives the magnitude of the work done by a constant electric field on a charge moving parallel to the field. That is, the work, absolute value of the work equals absolute value of the charge times ED. Okay. Let's back up. Okay, here we've substituted our definition of electric work into the work energy theorem. The electric force is conservative, so the electric work depends only on the endpoints of the path A and B, not the path taken. That means as the charge accelerates to the right in the figure, it gains kinetic energy and loses an equal amount of potential energy. As you remember, the work done by a conservative force can be reinterpreted as the negative of the change in the potential energy associated with the force. So the change in the electric potential energy of a system consisting of an object of charge Q moving through a displacement delta X in a constant electric field is given by the equation here. where E sub x is the x component of the electric field and delta x displacement of the charge along the x-axis. Even though potential energy can be defined for any electric field, this equation is valid only for the case of a uniform, which means constant, electric field for a particle that undergoes a displacement along the given axis, here called the x-axis. Because the electric field is conservative, the change in potential energy doesn't depend on the path. So it doesn't matter if the charge stays on the axis all the time, the change in potential energy will be the same. Okay, take a look at these two figures, which shows you a comparison of the electric and gravitational fields. As you can see, both fields are directed downwards. We see that positive charge in an electric field acts very much like mass in a gravity field. A positive charge at point A falls in the direction of the electric field, just like a positive mass falls in the direction of the gravity field. Let's let point B be the 0 point for potential energy in both figures. From conservation of energy in falling from point A to point B, the positive charge gains kinetic energy equal in magnitude to the loss of electric potential energy. The absolute value signs on Q are there just to make it explicit that the charge is positive in this case. In a similar way, the mass in the right-hand figure gains kinetic energy equal in magnitude to the loss of gravitational potential energy. So for positive charges, you can see that electric potential energy works very much like gravitational potential energy. In both cases, moving an object opposite the direction of the field results in a gain of potential energy. And when the objects are released, the potential energy is converted to the object's kinetic energy. One major difference between electric and gravitational potential energy is that there are two kinds of electric charge, positive and negative, but gravity has only positive gravitational charge or mass. A negatively charged particle at rest at point A in the figure would have to be pushed down to point B. To see why, let's apply the work-energy theorem. Let's apply the work-energy theorem to a negative charge at rest at point A and assume to have some speed v on arriving at point B. Notice that the negative charge had a positive change in electric potential energy in moving from point A to point B. If the negative charge has any speed at point B, the kinetic energy corresponds to that speed is also positive. The kinetic energy corresponding to that speed is also positive. Because both terms on the right-hand side of the work-energy equation are positive, there is no way of getting the negative charge from point A to point B without doing positive work W on it. In fact, if the negative charge is simply released at point A, it will fall upwards against the direction of the field. Let's define an electric potential difference, delta V, between points A and B as the change in electric potential energy as a charge Q moves from A to B divided by the charge Q related to the potential energy. Because electric potential energy is a scalar quantity, electric potential energy is also a scalar quantity. Electric potential is also a scalar quantity. From this equation, you can see that electric potential difference is a measure of the change in electric potential energy per unit charge. You can also think of the electric potential difference as the work per unit charge that would have to be done by some force to move a charge from point A to point B in the electric field. Take a look at the units. 1 joule of work must be done to move a 1 coulomb charge between 2 points that are at a potential difference of 1 V. That's a volt, 1 volt. In the presence of moving through a potential difference of 1 volt, the 1 coulomb charge gains 1 joule of energy. For the special case of a uniform electric field, like the field between charged parallel plates, we can divide our potential energy equation by Q to get the equation shown here. The result shows that potential difference also has units of electric field times distance. That means the SI unit of the electric field, the Newton per Coulomb, can also be expressed as volts per meter. Remember that this equation for delta Vx is valid only for the system consisting of a uniform electric field and a charge moving in one dimension. Released from rest, positive charges accelerate spontaneously from regions of high potential to low potential. If a positive charge is given some initial velocity in the direction of high potential, it can move in that direction, but will slow and finally turn around, just like a ball tossed upwards in a gravity field. Negative charges do exactly the opposite. Released from rest, they accelerate from regions of low potential toward regions of high potential. Work must be done on negative charges to make them go in the direction of lower electric potential. Okay, that ends this section. The next section we'll cover is section 16.2, electric potential.